Good day everyone. Today we will be discussing how to determine natural frequency of damped single degree of freedom system as part of the course Me22088. My name is Dr. C. Sendamarikanan. I am Associate Professor in the Department of Mechanical Engineering at SVC. Today we are going to explore the dynamics of a rotational system. Imagine a rigid board free to rotate about a pivot point at one end. Attached to this bar at a distance A from the pivot, we have a spring and a damper. At the other end, at a distance B from the pivot, is a weight W. Our goal is to derive the equation of motion for this system. That equation will describe how the system behaves over a period of time, particularly the rotational motion of the bar. To start, let's define some parameters. The mass of the weight is given as 1.5 kg, spring has a stiffness K of 4900 newtons per meter. The distances A and B are 6 cm and 4 cm respectively. We also have a damper with a damping coefficient C, which we need to determine for critical damping. Let us consider the downward angular displacement theta of the weight W. When we consider that, let I draw that, it is going to be the downward displacement of this bar like this. So it is theta. The displacement is theta. The angular displacement which will cause the spring and damper to stretch also compress. Displacement of the spring is simply A times the theta. This means spring force is K times A theta. Similarly, the velocity of the damper is A times the angular velocity, which is the derivative of theta with respect to time. Now we are going to substitute and find the equation of motion. Let me go for our Newton's principle itself. In that case, to derive the equation of motion, we need to consider the torque acting on the system. The torque due to the spring is the spring force times the distance, which is Ka theta times A. Then it will become as Ka square theta. Torque due to the damper is the damping force times A, which is Ca theta dot, which will become as Ca square theta. Torque due to the weight is the weight times the B, that is Wb. That can be rewritten for the moment of inertia W by G B square, where B is the distance from the pivot to the weight. Substituting this into the equation, we will get the equation of motion. Dividing throughout by W by G into B square, we arrive at the standard form of a second order differential equation, that is theta double dot acceleration, and this part is representing the velocity and this part is representing the displacement. To solve this equation, we use the quadratic formula in the next slide. In the previous slide, we arrive at the standard form of a second order differential equation. That equation describes the angular displacement theta as a function of time. To solve that, we use the quadratic formula. The solutions for the theta are given as there are two roots. So theta 1 comma 2, it will be minus b plus or minus root of b square minus 4ac divided by 2a formula. So by substituting it, we will get the solution. This means the two solutions of theta are identical, resulting in the fastest return to equilibrium without oscillation. Now let's setting the radical to 0. That means this is equal to that. So solving for Cc, we can able to get the critical damping coefficient. If we equate this, we can able to get the critical damping coefficient. So let you see that it is going to be here, putting left hand side equal to right hand side. What will happen? We will get A, B will get cancelled. Is it not? So there will be one A will get cancelled. There will be one B will get cancelled. This A, B will get cancelled. Similarly, G, G will get cancelled. So at last what will happen means if we rearrange it, then we will get this CC value. This CC value equal to 2B by A root of weight into K divided by G. Once again, if we further rearrange, that is substituting W equal to M into G, now we will get the formula for the critical damping coefficient as 2B by A root of Km. Now let's plug the given value, that is B equal to 4 centimeter, sorry, it is 14 centimeter, A equal to 6 centimeter, K equal to 4900 Newton per meter, and M equal to 1.5 kg. Substituting all this value, we will get the critical damping coefficient, which amounts to 400 Newton second per meter. Therefore, critical damping coefficient for the given system is 400 Newton second per meter. This means that if the damping coefficient C is set to this value, the system will return to equilibrium as quickly as possible without oscillating. This step-by-step procedure what we discussed demonstrates how to derive the equation of motion, solving it using the quadratic formula, and determine the critical damping coefficient for a damped rotational systems. In this slide, we are going to analyze a classic spring mass damper system, a fundamental concept in mechanics and vibration analysis. This system is a simplified model of many real-world scenarios, from car suspensions to building vibrations. We have a mass of 15 kilograms suspended by a spring stiffness 245 newtons per meter. In parallel with the spring, we have a damper, also known as a dashpot, with a damping coefficient C. The dashpot is a device that provides resistance to motion, typically proportional to the velocity. In this example, we are told that when a constant force of 49 Newton is applied to the piston of the dashpot, its velocity is found to be constant at 0.12 meters per second. So, we have to determine the value of damping coefficient. Also, we need to predict the complete system whether it will be a periodic or aperiodic. Let's start with the first part. We know that the damping force is related to damping coefficient and the velocity by the equation, that is force equals C times of velocity. Now we rearrange it such a way that we can able to calculate the C. It is given that as per the problem, spring mass system is going to be having a force of 49 Newton, velocity represented as x dot 0.12 meter per second, spring constant K equal to 245 Newton per meter, that is mass equal to 15 kg. Plugging all this value, we will get C equals to 49 Newtons, that is 49 is going to be the force value, divided by 0.12 meter per second, that is the velocity value. Calculating this 49 by 0.12, we find that C, that is the viscous damping coefficient, is approximately 408.33 Newton seconds per meter. In the previous slide, we calculated the viscous damping coefficient. Now, in this slide, we are going to calculate the undamped natural frequency using the formula natural frequency omega n, that is equal to square root of K stiffness divided by M. Plugging the values of stiffness and mass. Stiffness is 245 and the mass is 15 kg. If it is divided and taken the root, we will get 4.04 radians per second. And then we write the general equation, that is mx double dot plus cx dot plus kx equal to c. That is, equation describes system's displacement over a period of time. To determine this damping ratio, we can use the formula, that is C divided by 2m omega n. We know the values, all these values C, m, omega n. If we substituted, we can able to get 3.36. See that damping ratio is greater than 1. That means that if displace the mass and release it, it will return to its equilibrium without any oscillating. The motion will be aperiodic in nature. So we successfully calculated the damping coefficient C and determined that the system is overdamped and exhibits aperiodic motion. This example clearly demonstrates how to analyze a spring mass damper system and predicts its behavior based on the given parameters. We are going to explore some essential formulas used to analyze damped vibrations. These formulas helps us to understand how damping affects the behavior of oscillating system, like a mass on a spring with a dashpot, or even the vibrations of a building during an earthquake. Let's start with the damping factor or damping ratio, often represented by Greek letter zeta. This dimensionless quantity tells us how quickly the oscillations in a system will decay. We can calculate the damping factor in a couple of ways. First, it is the ratio of actual damping coefficient C to the critical damping coefficient Cc. Critical damping is the level of damping that allows the system to return to equilibrium as quickly as possible without oscillating. Alternatively, we can express the damping factor as C divided by 2m omega n, where m is the mass and omega n is the undamped natural frequency of the system. Now let's look at the damped natural frequency. This is the frequency at which the system oscillates when damping is present. It is related to the damped period Tp, which is the time it takes for one complete oscillation. The damped natural frequency can also be expressed as omega d divided by 2 pi, where omega d is the damped angular frequency. Next, we have the logarithmic decrement. This tells us how quickly the amplitude of oscillations decreases from one cycle to the next. Mathematically, it is the natural algorithm of the ratio of two successive amplitudes xn and xn plus 1. It can also be expressed in terms of the damping factor as 2 pi zeta. We can also relate the logarithmic decrement to the damping coefficient and the damped natural frequency as shown in the previous formulas. Finally, we are going to have the formula for the damped angular natural frequency, and which is going to be related with the term A. Omega d is calculated as the square root of omega n square minus a square, where A is equal to C divided by 2m. These formulas are fundamental tools for analyzing and understanding the behavior of damped vibration systems. By using them, we can predict the system response, design systems to minimize unwanted vibrations, and gain deeper insights into the dynamics of oscillating systems in various fields of engineering and science. Remember, understanding these formulas is key to mastering the concepts of damped vibrations. We already derived all these equations in our previous lessons. Please go through it for how to derive this logarithmic decrement and damping factor. We are diving deeper into the concept of logarithmic decrement and its connection to the damping ratio. These are crucial tools for understanding how damping affects the behavior of vibrating systems. Let's begin with the logarithmic decrement denoted by Greek letter delta. It provides a measure of how quickly the amplitude of oscillations decreases from one cycle to the next. Logarithmic decrement can be calculated using the formula delta equals the natural logarithm of the ratio of two successive amplitudes x1 and x2, but that's not at all. It can also be expressed in terms of the damping ratio zeta, undamped natural frequency, and the damped period. We see delta equals to zeta omega n time period, which can be further expanded to 2 pi zeta divided by square root of 1 minus zeta squared. We can also express it as 2 pi times c divided by 2 m omega d, where c is the damping coefficient, omega d is the damped natural frequency. Now look at a special case for smaller damping where zeta is much less than 1. We have a simplified formula. Delta is approximately equal to 2 pi zeta. This approximation is very useful when dealing with systems that have relatively low damping. It is important to note that logarithmic decrement is dimensionless and it is closely related to the dimensionless damping ratio zeta. In fact, it is essentially another way to express it. We can calculate the damping ratio zeta using the formula given below. It is nothing but zeta equals to delta divided by square root of 2 pi squared plus delta squared. This formula allows us to determine the damping ratio if we know the logarithmic decrement. In essence, logarithmic decrement and the damping ratio are interconnected. They provide valuable insights into the damping characteristics of a vibrating system. Understanding this relationship is very much crucial for analyzing and designing systems where damping plays a significant role. Let's analyze a damped spring mass system once again. We will calculate the natural frequency, damping coefficient and critical damping coefficient. First, we calculate the undamped natural frequency. This is the frequency at which system will oscillate when there is no damping. Let me see the problem. We have given that spring constant is 200 Newton per meter and the mass is 5 kg. When we using these values into the formula, we get natural frequency equals the square root of 200 divided by 5, which is approximately 6.32 radians per second. Next, we calculate the damping coefficient. This tells us how much the system is damped. We are given that damping force is 0.002 at a velocity of 0.01 meter per second. The damping force is equal to the damping coefficient times the velocity. So we can solve for the damping coefficient by dividing the damping force by the velocity. This gives us a damping coefficient value of 0.2 Newton second per meter. Finally, we calculate critical damping coefficient. This is the amount of damping that prevents the system from oscillating, returns it to equilibrium as quickly as possible. The formula is given here, that is 2 times mass and undamped natural frequency. Plugging the given values, we can able to calculate the CC, critical damping coefficient, that is approximately equal to 63.2 Newton second per meter. So we have calculated undamped natural frequency, damping coefficient, critical damping coefficient. These values help us to understand the behavior of the damped spring mass system. The next slide, we will able to calculate the ratio at which the amplitude of vibration will be reduced. We are continuing our analysis from the previous slide. Now that we have a damping coefficient and critical damping coefficient, first we will calculate the damping ratio denoted by the Greek letter epsilon. This dimensionless quantity tells us how much damping is present in the system. related to the critical damping. It is calculated by dividing actual damping coefficient by the critical damping coefficient. So in the previous slide we calculated C is 0.2 and CC is 63.2. By using this value we can able to find that the damping ratio is 3.16 to the 10 to the power of minus 3. This value indicates that the system is lightly damped. Next, we will calculate the logarithmic decrement denoted by the Greek letter delta. This parameter describes how quickly the amplitude of oscillations decreases over time. Let we calculate this using our previous values. Okay, that we already calculated damping ratio. So using that value, we can able to calculate the logarithmic decrement. So let we use that previous value, that is 3.16 into 10 power minus 3 here, substituting it appropriately in the denominator as well as numerator. This logarithmic decrement delta value is given as 0.0198. This value indicates slow decay of oscillations, which is consistent with our finding that the system is. So in the last slide, we came to a conclusion that what we calculated, that is logarithmic decrement, the value is very much less, that is 0.0198. We concluded it is lightly damped. Next, we are going to find a relationship, that is logarithmic decrement with respect to the amplitude ratio. This relationship we can able to find out what is going to be the n times the natural logarithm x1 divided by xn plus 1. So using this we can able to calculate the number of cycles, how the logarithmic decrement used to find out the decaying time. So here in the problem we given that 5 cycles has been given. So n is 5. We want to find the ratio of the initial amplitude x1 to the amplitude after 5 cycles. So hence we can able to substitute in this formula, that is it is given delta we already calculated. After 5 times it is going to be, we have to calculate the initial value. So taking that, it is n plus 1 means it is n is already 5 plus 1, we have to substitute x6. So x1 by x6. In other words, we have to calculated the x1 using this formula, that will be amounts to 1.104. So we use the logarithmic decrement to determine the amplitude of the oscillations, which shows that it is decreases approximately to 90.6% of its initial value after 5 cycles. This demonstrates how the logarithmic decrement helps us quantify the decay of oscillations in a damped system. We are tackling a practical engineering problem, designing an under-damped shock absorber for a motorcycle. This type of shock absorber is crucial for providing a comfortable and stable ride, especially when encountering bumps on the roads. We have a motorcycle with a mass of 200 kilograms. The shock absorber consists of 2 springs in parallel, each with a stiffness of k by 2 and a damping mechanism. When the motorcycle hits a bump, the shock absorber is subjected to an initial vertical velocity. We want to design the shock absorber so that the resulting displacement time curve exhibits underdamped behavior as shown in the figure. Notice how the displacement oscillates around the equilibrium position, gradually decreasing in amplitude over a period of time. This is characteristics of underdamped systems. We have specific design requirements as per the problem. The damped period of vibration, the time it takes for one complete oscillation should be 2 seconds. Additionally, the amplitude x1 should be reduced to 1/4 in 1/2 cycle, meaning x 1.5 is equal to x1 divided by 4. Our goal is to find out necessary stiffness and damping constancy of this shock absorber to meet this requirement. We also need to determine minimum initial velocity that leads to a maximum displacement of 250 mm. We use the equation for the logarithmic decrement in terms of the damping ratio, equation for the damped period of vibration, time corresponding to maximum displacement for an undamped system, and envelope passing through maximum points of a underdamped system for solving this problem. Initially, we are given that amplitude x 1.5 is equal to x1 divided by 4. This means that x2 is, which is one full cycle later, is x 1.5 divided by 4, otherwise x1 divided by 16. Using this information, we can able to calculate the logarithmic decrement as the natural logarithm of x1 divided by x2, which is natural logarithm of 16. Just substitute this here. This gives us 2.7726. We also know that delta equal to 2 pi zeta divided by square root of 1 minus zeta square. Solving this, we can able to find out damping ratio, which is equal to 0.4037. Damped period we can able to calculate using that it is going to be 2 seconds, which is given. We can relate this to damped natural frequency and undamped natural frequency using this equation. By using this equation, we can able to solve it for omega n, because here time period we know and zeta we know. The only unknown is natural frequency. From solving this, we can able to get that natural frequency is 3.4338 radians per second. Now we calculate the critical damping constant using the formula Cc equal to 2m omega n, where m is the mass of the motorcycle, which is 200 kg. This gives us a critical damping constant of 1373.54 Newton seconds per meter. The damping constant is then calculated as zeta times Cc, which gives us 554.4981 Newton seconds per meter. Finally, we can able to calculate the stiffness for the motorcycle, which has given us 2358.26 Newton per meter. Therefore, required damping constant is approximately 554.5 Newton seconds per meter, and the required stiffness is approximately 2358 Newtons per meter. These values will ensure the shock absorber meets the specified design requirements for underdamped behavior and amplitude reduction. Now, let's take a look how to calculate the time at which the displacement of a mass reaches its maximum value in an underdamped system. We start with the equation, that is sine of omega d times t1 equals the square root of 1 minus zeta squared, where omega d represents the damped natural frequency. T1 represents the time at which maximum displacement occurs. Zeta is the damping ratio. In this specific problem, we are given that zeta is 0.4037. Plugging this value into the equation, we get sine of omega d times T1 square equals the square root of 1 minus 0.4037 squared, which calculates to 0.9149. We are also given that sine of omega d times T1 equals sine of pi times T1. So we can set sine of pi times T1 is equals to 0.9149. To solve T1, we take the inverse of this and divided by pi. This gives us T1 equals to 0.3678 seconds. Therefore, the displacement of the mass will attain its maximum value at time T1, which is 0.378 seconds. Let's continue with our analysis of the motorcycle shock absorber, we are now going to determine the initial velocity required to achieve a maximum displacement of 250 millimeters. We are given that the maximum displacement is 250 millimeters or otherwise it is 0.25 meters. The envelope passing through the maximum points is described by the equation x equals the square root of 1 minus zeta squared times x times e to the power of minus zeta omega nt. We know the value of zeta, that is 0.4037, and omega n is 3.4338, and we have calculated T1 in the last slide, that is amounts to 0.3678 second. Substituting this value into this equation, we can get 0.25 equals the square root of this values. When we substituted, we are solving for x, we find that it is equal to 0.4550 meters. Now let me go for velocity. The velocity of the mass can be obtained by differentiating the displacement equation with respect to time. At time t equals 0, velocity is simply x times the omega d, which is also equal to x times omega n times the square root of 1 minus zeta square. Plugging all the known values x, omega n, zeta square, we can able to calculate the velocity of mass. It is calculates to the value 1.4294 meters per second. Therefore, minimum initial velocity required to achieve a maximum displacement of 250 millimeter is 1.4294 meter per second. With this, we concluding this shock absorber for a motorcycle, we completely covered and determined stiffness, damping, all the values, so that the motorcycle can able to go for a underdamped motion. And what is the initial velocity required for that mass of 200 kg to give the initial velocity value 1.4294 meter per second. In the next slide, we will go for the next application problem. This schematic diagram of a large cannon is given here. When the gun is fired, high pressure gases accelerate the projectile inside the barrel to a very high velocity. The reaction force pushes the gun barrel in the direction opposite to that of the projectile. Since it is desirable to bring the gun barrel to rest in the shortest time without oscillation, it is made to translate backward against a critically damped spring damped system called the recoil mechanism. In a particular case, in this case, that is the gun barrel recoil mechanism have a mass of 500 kg with a spring stiffness of this 294 Newton per meter. The gun recoils at 1.3 meter upon firing. We have to find out critical damping coefficient of the damper, initial recoil velocity of the gun, and time taken by the gun to return to a position of 0.05 meter from its initial position. We are analyzing the recoil system of a gun barrel, treating it as a spring mass system with potential damping. We will be looking at the recoil velocity, the critical damping required, and the natural frequency of the recoil. At first, we are modeling the recoil process by equating kinetic energy of the recoiling barrel to the potential energy of the spring. This is based on principle of energy conservation. Accordingly, we have that kinetic energy of the barrel is of mx dot square equal to potential energy is of kx square. We have the mass, stiffness of the recoil spring, and maximum recoil distance. All these things we can substitute it here. Then we can able to achieve that the recoil velocity is 28.77 meter per second. This is the velocity the barrel reaches immediately after firing before the recoil mechanism starts to slow it down. Next, we are going to calculate the critical damping. This is the amount of damping required to bring the barrel back to its original position as quickly as possible without oscillating, preventing excessive recoil and ensuring stability for the next shot. The formula for critical damping, we already know that it is 2 times the square root of the spring constant times the mass. While substituting the stiffness and mass, plugging all the values here in this formula, we find that the critical damping required is 26,563 Newton seconds per meter. This is the crucial design parameter for the recoil mechanism so that the recoil mechanism will act properly. The next, we will calculating the natural frequency of the recoil system. This is the frequency at which the barrel would oscillate if there were no damping. The formula for natural frequency is given as square root of stiffness divided by mass. We know all the values, stiffness as well as mass. Substituting this value in this formula, we can able to find that natural frequency of the recoil system is 22.1 radians per second. This tells us about the inherent oscillation tendency of the barrel if not properly damped. So we calculated initial recoil velocity, critical damping required for optimal recoil control, and the natural frequency of the recoil system. These are the three critical parameters used for designing an effective and safe recoil mechanism in a gun barrel. Let's delve deeper into the analysis of our gun barrel recoil system, specifically focusing on the recoil time under critical damping conditions. First, we calculate the time period of the undamped oscillation. This is the time it would take for the barrel to complete one full oscillation if there were no damping. Using this formula, we can able to calculate that time period is 0.283 seconds. We are interested in the time it takes for the barrel to recoil, which we approximate as 1/4 of the time period. This because the recoil is essentially the barrel moving from initial position to its maximum displacement. This gives us a recoil time of 0.071 seconds. Now, let's look at the equation for displacement of the barrel under critical damping conditions. This given by x equals a1 plus a2t times e to the power of minus omega nt, where a1 and a2 are constants determined by the initial conditions. So initial conditions are at a time t equals to 0, displacement x is 1.3 meters and the velocity x dot is 0. Using these values and initial condition, we can able to find that a1 is equal to 1.3. We also find that a2 is equal to a1 times omega n, which is amounts to 28.7. Therefore, under critical damping, it takes approximately 0.22 seconds for the barrel to recoil. This one we will calculate in the next slide. In the previous slide, we calculated A1, A2 constant. A1 is 1.3, A2 is 2.7, omega n natural frequency is 22.1. We substituted in the motion equation. Okay, after that we have to find out what is going to be the T. We have the equation which is describing the displacement x of the gun barrel as a function of time t, which is given in this form. To find time t, when the displacement is going to be given already, it is 0.05 meter, x is 0.05 meter, which is already given. So for that, we have to go for trial and error method. Let me go for substituting t with different seconds. So we put up a tabular column. We are using different values of t's to calculate this part by part. We are calculating the equation. At last we are calculating what is x. When we substituting t equal to 0.1, this is trial and error method. Keep it in mind. So when t is 0.1 seconds, x is equal to 0.46. Similarly, when t is goes on 0.2, 0.21, 0.22, the x value is reaching to 0.049. So this means the closest value is 0.05 meters, which is closest when the t is reaching to 0.22 seconds. Therefore, we can approximate that the time taken for the gun barrel to return to a position 0.05 meters from its initial position is 0.22 seconds. See that gun barrel is reaching to the initial position just 0.22 seconds. However, this indicates there is another time component also to be taken into account. Okay, so we have to add the previous time component, that is 0.071 second. This additional time is related to the recoil time. Recoil time we already calculated in the previous slide. So this recoil time and this 0.22 both should to be added together. Therefore, the total time taken for the barrel to initial position is going to be 0.29 seconds. This approach, as we discussed, is a very practical example, allows us to approximate the solution to the equation and understand the time taken for the gun barrel to return to a specific position during its recoil mechanism. We have just wrapped up thorough exploration of Unit 1 focusing on single degree of freedom systems. We have delved into both undamped and damped vibrations, learning how to determine natural frequencies and analyze the system behaviors. Just to conclusion, let me recall the gun recoil problem we concluded just now. We applied our knowledge of critical damping to analyze the barrel's motion. We derived the equation of motion and even used a numerical approach to approximate the time taken for the barrel to return to its specific position. This examples highlights the power of single degree of freedom analysis. We are able to model a complex physical phenomena using a simplified system and gaining valuable insights. Now we are ready to move on to Unit 2, where we will explore more complex and realistic scenarios. We will be expanding our understanding of vibrations by introducing two concepts: forced vibrations and 2 degree of freedom systems. Thank you.